Okay, so we want to just get a little practice with this. So just pretend I'm doing this demonstration. So here's a cart, string, frictionless, massless pulley, string with a mass. And just we want to ignore friction, all right? So we're holding this cart, and then we let go. Okay, so we let go. Okay, so if we were in class, we would discuss this all together. So pretend you're discussing it with me, all right? Okay, so remember, initially I'm holding it at rest, and then I let go. So number one, does the kinetic energy of the cart increase or decrease? Well, obviously it was at rest, and now it's going to start moving. So it increases. What is the sign of delta K? Well, again, delta K is K final minus K initial. K final is positive. I mean, K is always positive. K initial was 0, so delta K is positive. Delta K is positive. The kinetic energy increased. 3. What are the forces? What are the forces acting on the cart? Well, you know, normal, weight, tension. So normal, weight, tension. 4. For each of the forces, is the work positive, negative, or 0? All right. The cart's moving in this way direction. What's the work done by the normal force? Can the normal force change the speed? Of course not. All right? I mean, so you know the work is 0, or you can just go by the definition. What's the angle between the normal force and the ds? 90. What's cosine of 90? 0. Okay. So the work done by the normal force is 0. Well, how about gravity? Same thing, right? I'm going to put G for gravity, okay? Because too many W's. All right. That looks stupid too. I'll put mg. I'll just do this. Fg. Yeah. All right. Force of gravity. So ds is this way. Force of gravity is that way. Angle is 90. Work is 0. So the work done by the force of gravity equals 0. Now, how about the tension? Well, the ds is this way. The tension force is this way, so it's positive, right? It's positive. The angle is 0. So the work done by the tension is positive. Okay, and we explained it already, so 4 or 5. Okay, 6. Is the net work positive, negative, or 0? Well, that's 0, that's positive, so the total work, or the net work, is greater than 0. 7. Does that agree with delta K? So what we're saying is, remember, there's the equation is this, right? So we have delta K positive, and the work is positive, so yeah, it agrees. Yay! Okay, it agrees, all right? That's all. All right, so that hopefully made some sense. Okay, now we want to ask the same questions, but we want to change the demo a little bit. Okay, so what we're going to do now is we're going to push the cart away, okay? So we're going to push the cart away from the pulley, right? We're going to push the cart away from the pulley, and so obviously, so the mass is going to, be lifted up, right? And so we're going to push it away and let go, okay? So, we push it this way and let go. What's going to happen? It's going to slow down, it's going to stop, and it's going to reverse. But all we want to look at is after I let go, so after the release and before it stops. Okay? So basically, what's it doing? It's just slowing down, right? So in other words, it's while it's slowing down. Okay, so here we go. So what? Okay, so does the cart increase or decrease? Does the K of the cart increase or decrease? Well, it's slowing down, right? So it decreases. 2. What's the sign of delta K? Negative. Because delta K is K final minus K initial, and it's slowing down, so it's negative. 3. What are the forces? Same as before, right? There's a normal, there's a force of gravity, and there's the tension. Okay, for each of the forces, is the work positive, negative, or zero? Well, same as before, right? Well, somewhat. The work done by the normal is zero because the normal is perpendicular to the direction of motion. The work done by the force of gravity is also zero for the same reason. Now, the thing is going this way. The tension is pulling that way. So that means the velocity is this way, but the acceleration is that way, right? Because it's slowing down. So that means that the force is that way, right? The tension force is that way. So what's the angle between the ds, or the dx, and the tension? 180. So what's cosine of 180? -1. So what's the sign of the work done by tension? It's negative, right? I mean, the thing's going this way, tension is slowing it down. So it's negative work, it slows down. It doesn't make it go faster, it makes it go slower. Okay, so 6. What's the sign of the net work? 0, 0, negative, so the net work is less than 0. 7, W equals delta K. So work is negative, delta K is negative. Yay! It agrees. Right, it agrees. Okay, that's all. Just to make sure you understand all the signs and everything. Okay, so here's another way of trying to figure this out. So here's the object. It's moving to the right. You apply a force to the right, so it's going to go faster. No kidding, right? So there's a before and an after, and it's going faster after than before. So work is positive when the work is in the direction of motion. The force causes the object to speed up. Energy is transferred from the environment to the system. The system's energy, therefore, increases. So this is what I like to think of. It helps, right? If this thing, wants to move, so positive work, it helps. It makes it go faster. Think of riding a bike down a hill. Gravity helps you go faster. Positive work. On the other hand, here the thing is moving to the right, force is applied to the left. Right? Okay, so before and after. Velocity is fast, then it slows down. Work is negative when the force is opposite to the motion. The force causes the object to slow down. Energy is transferred from the system to the environment. The system's energy decreases, so I just say it hurts. So I think of riding a bike up a hill. Is gravity making it easy or difficult? Difficult, right? So it's negative work. It hurts. All right, that's how I look at it. So there is my, So does gravity help or hurt? When you're going up a hill, it hurts. So it's negative work, all right? It's negative work. All right.
Is that you?
No. Google Images. All right, so this is a question, and I'm being really picky, and I'm being picky for a reason, okay? I'm trying to get a point across. I exert a 10 Newton force on a crate, and it moves 5 meters. What's the work? So pause your video and figure it out. Okay, you should all be confused, right? Honestly, you should all be confused right now. Why should you be confused? Because calculate the work. What are you talking about? I mean, work is done by a force, right? And so do you want to calculate the work done by, me or the friction, or do you want the network? I mean, you can't just say work, right? That's what I mean. I'm being picky, right? So you gotta put an adjective here, or something. The work, or you can't just say work. You gotta specify the work done by this force or that force or the total force or what. Okay? So it's a ridiculous question. All right? That's what I'm trying to get across. Ridiculous question. All right, so let's make it not ridiculous. Okay, so calculate the work done on the crate by me. All right, so pause your video and figure it out. Okay, now notice we have, okay, we're back. So we have constant force, right? I mean, here's the definition. Right? Okay, so, but here we have, constant force, right? and everything's either parallel or anti-parallel, you know. So basically we just have this, right? That's what we have because it's constant force. Okay, so the work done by me, well, the force is 10 newtons, right? And it moves 5 meters in this direction. So the angle is 0, cosine of 0 is 1. So it's just 10 newtons times 5 meters, which is 50 Newton meters, or 50 joules. Okay, so that's 50 joules. Positive, right? Made it go faster. The acceleration was to the right. Okay, now let's calculate the work done on the crate by friction. Now, does friction make it go faster or slower? It's pretty obvious. It goes slower. So it's going to be negative. Why is it going to be negative? Because what's the angle? I mean, the displacement is this way, but the friction force is that way. And what's the angle? 180. What's cosine of 180? Negative 1. So the work done by friction, okay, the magnitude of the force is 5 newtons. It goes 5 meters, but then we have cos 180, which is negative 1. So we just have negative 25 joules. Negative 25 joules. All righty. Okay, any other forces that we care about? What's the work done by the normal force? 0, right, because 90 degrees. What's the work done by the gravity? 0, because it's 90 degrees. So what's the total work? Well, it's 50 minus 25, 0 and 0, right? So the net work is just 25, right? So the net work is just 25 joules. And we could have saved ourselves a lot of trouble by just calculating the net force and just use the net force dotted with the displacement. But it's all right. I want to do it this way. Okay, let's do some more complicated problems. A 200-gram ball is lifted upward on a string. It goes from rest to a speed of 2 meters per second in a distance of 1 meter. What is the tension in the string? Oh, all right. Now, I gave you the hint, you know, use the W net equals delta K. But let's say I didn't do that. You know, let's say this is a final exam. And, you know, it says, what's the tension? So that's force, right? So you're thinking maybe force diagram. But then, you know, it says speed and distance. And so you're thinking, wait a minute, this kind of sounds like kinematics, but, oh, I don't know. So, I mean, in my opinion, this is how you kind of want to think of this. So the ball is at rest, and then it goes to a certain speed. So there's an initial kinetic energy, there's a final kinetic energy. So in your head, or initial speed, final speed, yeah. I think whenever you see speed, you should think kinetic energy. Now later on, we're going to learn something else, but momentum, and that's fine. But right now, if you see speed, you think kinetic energy. So right now, when I'm reading that problem, I'm thinking there's an initial kinetic energy, there's a final kinetic energy, right? There's a before and an after. Initial K, final K. Okay, we want to know a force, right? We want to know what a force is. And we know there's some displacement, like a delta X or delta Y or something like that, you know? So what equation or what principle has, you know, delta K and a force and a displacement? Right there, right? Because work is a force dotted with a displacement, and delta K is, you know, the delta K. All right? So that's kind of like the thought process you want to go through. All right? And again, as soon as you see that initial K and a final K, bingo, you know, you have the delta K. So I would try that first. It might not work, but I mean, that's where I would try it first. Because this is a whole lot less work than doing force diagrams and kinematics, you know? I mean, you just do it. Okay, so let's do it, right? I just said, let's do it, all right? Okay. All right, so the net work equals delta K, right? Delta K. And so what is the net work? Okay, so I'm going to draw a force diagram. Sorry, it's part of my being, you know. What are the forces acting on the ball? We have gravity, and we have tension, right? All right. So what's the net work? The net work, using a radii coordinate system, is tension minus gravity. That's not so bad. So tension minus gravity, minus force of gravity. Again, they're both forces, right? So T minus mg. Oh, wait a minute. Okay. And then it's work. So it's delta y, right? Delta x, delta y, whatever. And notice I incorporated the sign, right? So the work done by tension is T delta y. The work done by gravity is mg delta y times minus 1, right? Because look at the delta y is this way, force of gravity is this way, the angle between it is 180, cos 180 is negative 1. All right, so I incorporated the minus sign already. Okay, so T minus mg delta y, I should have written it like this, I guess. T delta y minus mg delta y, right? But that's the same as that. Okay, and what does that equal? Delta K. Now, delta K is K final minus K initial. It started out at rest, so we just have K final. What's K final? It's 1/2 mv final squared, right? Okay, so all right, let's multiply it out. So T delta y minus mg delta y equals 1/2 mv final squared. I want to get T, so I want this on the other side, so I'm going to add it on the other side. There. So I add it on the other side. Now I divide by my delta y. And that's it. All right, that's it. I promise you, if you plug in all the numbers, you get 2.36 joules. I mean, no, newtons. It's a force, or silly rabbit. Okay, that's all. Right? So isn't that nice? I mean, that's pretty simple, you got to admit. It's much, much less work than kinematics and all those F equals ma problems, you know? Right? So W net equals delta K. Okay, let's do another one. Oh, this looks worse. Ugh. You see a 1,000-kilogram car rolling slowly across a level surface at 1 meter per second. So it's not so fast. It's not going to kill you, right? Heading toward a group of small children. Oh, that's not good. The doors are locked, so you can't get inside to use the brakes. Instead, you run in front of the car and push it with a constant force on the hood at an angle of 30 degrees below the horizontal. How hard must you push to stop the car in a distance of 2 meters? Now again, I wish I wouldn't have written this here. But so what's your thought process? Okay, so your thought process, you know, K final is 0, right? You're going to stop it, and you have some K initial, whatever that is. It's not 0, right? So in other words, you have a before, you have after. K initial, K final. Now the question is asking about a force. And it says you want to stop it in 2 meters. So there's a delta x. So again, what equation or what principle have you learned that relates delta k force delta x? This, right? So that's kind of why you want to think of that, right? So as soon as you see a force and a displacement, in your head you're thinking work, work, all right? Force times the displacement is work. So that's awesome. Okay. So that's kind of what you want to do. All right, let's do it. So we have, you know, work equals F dot delta x. Now notice, I've been nice so far, right? We've only had constant forces, so we haven't had to do any integrals, you know? So that's kind of nice, right? Okay, now we've got to be better draw a picture, right? Oh boy. So here's my great picture. Okay. So there's the horizontal, and there's, let's say that's F. So there's F, and that's 30 degrees, right? Because it says that you're applying F at 30 degrees below the horizontal, right? 30 degrees below the horizontal. All right, we can do this. Okay, so here we go. Ready? So F dot delta X, that's F delta X cos theta, right? And again, it's K final. All right, so that's equal to delta K, which is K final minus K initial. But what's K final? Hopefully 0, right? You're going to stop the car. So that's 0. So we just have F delta X cos theta equals minus K initial equals minus 1/2 mv initial squared. Now, we only care about the magnitude, right? I mean, we know what the direction is going to be. All we care about is the magnitude of the force, you know. So I'm just going to get rid of the minus sign because I don't care, because I just want the magnitude, you know. I don't care about, I know what the direction is going to be. So we want to solve for the force, so all we have to do is divide by this. Okay, so let's do it. Why not? 1/2, mass is 1,000 kilograms. Velocity initial, what's that? 1 meter per second squared. Delta X is 2 meters. Cosine theta, cosine 30 degrees. You work that out, and you get 288.7 newtons. Okay? Now, let me just notice something here. So, you notice that the force is proportional to the mass. So if it's a heavy car, it's going to be hard to stop it, right? But also the force is proportional to the velocity squared, right? So if that car has an appreciable velocity, man, it's going to be really, really hard to stop it. Okay? So just be aware of that, all right? All right, let's do one more. Let's do one more. Let's not do one more. Hold on a second. Yeah, let's do this one. Okay, a 1 kilogram block moves to the right along the x-axis. It passes x equals 0 with a velocity of 2 meters per second. It is then subjected to the force shown in the graph. All right, so it's going at 2 meters per second, and then it's subjected to this wacko force, right? All right? All right. So which of the following statements is true? And I keep being too nice. Okay, why would you want to use that? Well, you got to admit, as soon as you see a force versus x graph, what do you think of? You better think of work, you know, because work is the integral of f dot dx. So the area under the curve gives you the work, right? So fx graph work, all right? Then you see a velocity, and then these questions are about velocity, and so you say work before and after, initial velocity, final velocity, initial kinetic energy, final kinetic energy. It's right there. This is it, right? Everything that's incorporated right in that little equation. Okay? All right, so you figure it out. So pause your video and figure it out. By the way, you don't have to do a single calculation. So you can just put your hand in behind your back. No math at all. Well, I mean, you have to do a little bit of mental math, but not a whole lot. Okay, let's answer the question. All right. So we know that the net work equals delta K, which is K final minus K initial. And we also know that the net work is integral F dot dx, which is the area under the curve, right? Area under the force x curve. Okay, so this is considered positive. This is considered negative. Obviously, this area is larger than this area, so the total work is positive. If the total work, so this is greater than 0. That means that this is greater than 0. That means that this is greater than 0. That means that K final, oops, funny looking K final is greater than K initial. And that's all you really need to do, okay? So initially it was going at 2 meters per second. Since it was positive work, it goes faster than 2 meters per second. So the answer is that one, right? The block gets to x equals 5 meters with a speed greater than 2 meters per second. All right. Okay, let's do that. Let's see, do I want to do that? I don't want to do that one. Okay, let's quit.